Hi, I'm Guang, 50 years old. In this lesson, we'll be taking a look at the techniques and applications of definite integrals. And we'll explore different types of methods you can use for different types of integrations. Well, of course, there are going to be many different techniques that you can use. For example, we can take a look at this question. This question seems a bit different from what we have done before, since now you do realize there is a limit. R approaches to 0. So, limit R approaches to 0. 1 over pi r squared, double integration with the boundary of x squared plus y squared is smaller or equals to r squared, and your integrand of e to the power of x squared plus y squared cosine x plus y dx dy. So, if you do not know any of these strategies and you look at this question, you might not know how to solve it, since this seems very complicated. You have double integration, you have exponential trigonometry within your boundary of a circle, and you have limits. How on earth are you ever going to solve this? It seems impossible, isn't it? But since it's definite integration, we do have some strategies, some special methods we could use to solve this. And let us take a look at what exactly are these methods. So, firstly, you see this kind of circle and you see x squared plus y squared. The first thing you should be thinking of is change it to polar coordinates. And that is exactly what we are going to have over here. Alright? So, when we change this into polar coordinates, what will we see? So when you have polar coordinates, you have e to the power of r squared cosine r cosine theta plus r sine theta, and then r d theta. Alright? So apparently in this form you still can't solve it, even though you might think, well, now I've changed the polar coordinates, there has to be something that we can do, right? But no, in this state, you still can't solve it. Now what do? Well, in this case, we do have a very special method. And this special method is also very, well, how should I put it? You can only use it in some cases. Well, generally, you wouldn't think of using this method. So what exactly is this method? That would be a squeeze theorem. Now, you could remember that we have talked about squeeze theorem before in other cases, like limits. In this case, we can once again use the squeeze theorem. But it seems a little sketchy, isn't it? So how are we going to use our squeeze theorem? Firstly, we take a look at cosine. Cosine is our main problem here. If we could somehow get rid of that cosine, maybe things will be much easier. We can see. So, remove the cosine. Well, let's think about a maximum value for cosine. A maximum value for cosine is 1, of course. So how about let's take a look at what if that cosine is just 1, alright? So this is basically what you will get. Now what can we do with this part? We will just proceed with our normal double integration process. What is this range that you see? So this range that you have, a circle centered at 0, 0 with a radius of r. So when you integrate with respect to r, it will go from 0 to r. But beware, these two r's are kind of different, since one would be a fixed, well, you wouldn't really be a fixed value, it's just used in this limit, while the other is used for your integration, alright? So 0 to r, that's your radius, and of course a circle. So that means your theta would be from 0 to 2 pi. Okay, so this is what we will have. So this part inside, it is pretty simple to integrate, isn't it? You just put the r inside and then you can integrate it. So 1 over 2 pi r square, and you will be seeing e to the power of r square, substitute in 0 and r. Since when you put that in, you have a dr square with an actual half in front, and dr square, well, if you know the integration of e to the power of x dx, that would be simple. Okay, so this is what you'll see when you integrate for r. Well, for r, it's pretty much all the other terms, right? And what you're left with is just integrate from 0 to 2 pi d theta, which will just give you a theta to substitute in the values 0 and 2 pi. Okay, so this is pretty much what you are going to see. Alright, so for the next part, which we are just going to substitute the values in, we will have limit r approaches to 0. So over 2 pi r square, this term, when you substitute in the two values, you will have e to the power of r square and then minus 1, since you substitute in 0, alright? And 0 is e to the power of 0, which is 1. And for your theta, it's just going to give you 2 pi. Okay? So, this part gives you 2 pi. Well, of course, minus 0, that part doesn't matter. Now, here, we can actually get an answer for this. So what exactly is this answer? Yes, you'll be removing these two pi's, and you'll be left with e to the power of r square over r square. But you might be wondering, how do we solve it? So if you have watched a few of the techniques of limit calculation videos, then you would probably know about the L'Hopital's rule, which in this case, you'll differentiate for r, okay? So differentiating for r, this term below, r square, just becomes 2r. Or in the numerator, you still have e to the power of r square, chain rule to get 2r in front. So all you're left with is e to the power of r square. And when you sub 0 into that, all you have is 1. Okay? So, alright. So now, we have kind of an overestimation for your original function here, right? Since a maximum value for cosine is 1, and that is exactly what we took over here. But next, you can proceed to look at your cosine term here. Now, can you think of anything about cosine that could possibly help us in this situation? Well, of course, since you want kind of an underestimation for this value that you have, you could use the Maclaurin series. So, how exactly to use the Maclaurin series? Now, in this Maclaurin series, what you can have is, now let's say we just use cosine x first, alright? So of course x later on will be replaced by this entire chain over here, but let's take a look at cosine x. What's the Maclaurin series for cosine x? That would be 1 minus x squared over 2 factorial plus x to the power of 4 over 4 factorial, and so on. You could have learned this in school. And you could have learned that, well, if you remove this part behind, that would be what you have as a small angle approximation. But you can also write this in a small o notation. So for the rest of the parts beyond the power of x squared, we are going to ignore them, alright? So things like x to the power of 4, x to the power of 6, we would ignore whatever they have, alright? So that means, since this part, it is mostly add on something. Wait, whoops, sorry. This is from power of 4 and beyond, right? Okay, so now since this is pretty much an add-on something, as the terms get smaller and smaller, when you add on something and you remove the something that's added on, you will be making the value smaller. So let's say your original integration is called a. So you have a smaller than or equals to whatever you have, and an a bigger or equals to limits r approaches to 0, 1 over pi r square. Double integration your boundary on the circle that you have, and then e to the power of r squared, and this is where we use what we just had. So you're going to see 1 minus r cosine theta plus r sine theta squared over 2, and then r dr d theta. Alright, so I'm just going to remove this part. Okay, so this is what we are going to have to solve. Now, we will determine the boundaries for them. Determining the boundaries should be pretty simple. So for r, it will be a 0 to r, while for your theta, it will be from 0 to 2 pi. Okay? Now, e to the power of r squared. Of course, you could also take out a half to make this a 2. Well, it depends on whatever you like to use, alright? Now, when we take a look at the term within here, you have r squared cosine squared theta plus 2r squared sine theta cosine theta and r squared sine squared theta. So when you expand it, this is going to be the part that you will see, alright? Which you can also change it into r squared plus, or you could also just take out the r squared and make it 1 plus sine 2 theta, alright? Since this part you can use a double angle, while for the rest of for the other two terms, you just use your identity, alright? So you could just change it into this form. Now, you have r squared 1 plus sine 2 theta. How about we have the parts with r together? Or can you think of any other way to separate the two portions with r and theta, alright? So how about we take out the 2 and we will be seeing 2r minus r cubed 1 plus sine 2 theta, and then dr d theta. Okay, so now that we have arrived at this state, what would you think that we can have? Now, since this is a minus, you can separate them into two separate terms to work on them separately. Why do you have to do that? Because you can realize that since you have a 2r, doesn't it sound familiar? Something about what we have done before? Well, of course, if you just have a e to the power of r squared with an r, which is similar to what we have up here, that means we could solve the first part. For the second part, we will see about that later. Okay, in your first term, that means you won't the 2, you can bring it out. So integrate from 0 to 2 pi, and then integrate from 0 to r, e to the power of r square, and you have r d theta, right? Okay. Well, for your second term, which you will be seeing minus 1 over 2 pi r square and integrate from 0 to 2 pi. Or you could also just bring out the 1 over 2 pi r square altogether. And just leave the 2 inside here. Alright? Should look more simpler in this way. Okay, so integrate 0 to r, and we'll have e to the power of r square, r cube, 1 plus sine 2 theta, dr d theta. Okay, now these are the 2 portions that we will be seeing. We can integrate the first part quite easily, as we will just put 2r within, and your theta would also integrate separately. Okay, so that's for your first part. Now when you take a look at the second part, it seems a bit more complicated, right? Although what you can have is 1 plus sine 2 theta. You can integrate that separately since it is independent of the r, and it is multiplied onto the other terms with r. So you can integrate this part with respect to theta first. Alright, so you are going to see limits. R approaches to 0. And you're going to have 1 over 2 pi r square. Now, the first term, you put them inside and you have e to the power of r square, which you can substitute in 0 and r, and of course your multiply onto theta, which you can substitute in 0 and 2 pi. Well, for the second term that you have, we are going to integrate 1 plus sine 2 theta first. So 1 plus sine 2 theta. 1, of course, you can already have the theta from it. So theta integrate from 0, substitute in the values from 0 to 2 pi. Now, sine 2 theta. Sine 2 theta, which means we can have, okay, I'm just going to write out everything. So half, integrate from 0 to 2 pi, sine 2 theta d 2 theta. Okay, so that will be for 1 plus sine 2 theta d theta. And the last part that you'll be seeing is, of course, your terms with r. Alright, so this is pretty much what you will be seeing. Looking at the first term, we have e to the power of r square minus 1. Multiplied by 2 pi. Well, for your term behind, actually you can also separate these into 2 separate limits, since, well, they just subtract each other. So sure, why not? You can separate them into these 2 limits, and then you have to subtract limit r approaches to 0. Now, since you have this part, so 2 pi, and then you have to add on, so sine, when integrated, it becomes a negative cosine. and you have to substitute in the values 0 and 2 pi. Alright, so then all that we have to deal with is your last term. Now the last term, it would require another special method in order to solve it, which I will talk about that a little later, right? Now, the first term, when you try to solve it, you have e to the power of r squared minus 1 over r squared, which is actually something that we have already done over there, which is 1, okay? So 1 minus something. So 1 minus. Now, let's take a look at cosine, the term with cosine, okay? Now, cosine 4 pi. So what is that? That would basically be a cosine 0, which is 1. And then you have to minus itself, which will just give the 2 pi from this previous term, okay? So, since it just gives the 2 pi from this previous term, we could simplify the 2 pi with this 2 pi, and we will be seeing one over r squared. And you have integrate from 0 to r e to the power of r squared r cubed dr. So in this case, we are going to use something that looks like a L'Hopital's rule, or some of you might just call it a Leibniz rule for this limit and integration part. Now, how does this work? Let's take a look at this. So 1 minus. Now, when you use this rule, you would obviously be aware that this is in a 0 over 0 form, okay? In this case, it is a 0 over 0 form. Now, in the numerator, you will have your upper boundary. Well, when you differentiate that with respect to r, it basically gives a 1, so that doesn't really matter. Now, inside your integrand, you will substitute in your boundaries. So, when you substitute in your upper boundary, you would actually still have your e to the power of r squared and r cubed. So e to the power of r squared and r cubed would still be up here, while in your denominator you are going to have 2r, just like your L'Hopital's rule. Alright, so at this state, can you see anything over here? So at this state, what you would realize is, how about let's simplify an r. So you see e to the power of r squared times r squared over 2. And it's no longer an indeterminable form, which means you can substitute in r equals 0. And when substituting that, this term behind is a 0. So at last, what you have is a 1, okay? So now, when you have something, this term that is smaller equals to 1, bigger equals to 1, what does this term have to be? Well, of course, that means this entire limit and integration here would be equal to 1. So you can have this entire thing again. Limit r approaches to 0, 1 over pi r squared, and you have your boundary. E to the power of x squared plus y squared cosine x plus y dx dy is equal to 1. Okay. So that would be pretty much all we'll see in this lesson, alright? Now, taking a look at what we just had. Firstly, we changed it from Cartesian coordinate into polar coordinate, and then in the polar coordinate form, we had your squeeze theorem. With your squeeze theorem, the first part you did some integration, and in the second part, you use a little bit of identity, you change them around a little bit, And finally, used a Leibniz rule in order to solve whatever you have. And by the squeeze theorem, whatever you have inside, since it is smaller or equals to and bigger or equals to the same thing, that means it is basically that thing. Alright, I'll be ending this lesson here, and thank you for your watching.